what we're going to start doing in Chapter 3 is calculating what's called a derivative. And you kind of started doing that already in the last chapter when you found an instantaneous rate of change. But a derivative is a general formula that works for any x value. You found it for a particular x value, is what you were doing. And what we're going to have to do in this next chapter is basically do the same stuff you were kind of doing, except instead of putting a number in for where a was, you're going to put an x in there. And so these can get kind of big, especially if you start cubing something or taking it to the fourth or fifth. But it is a binomial, right? If it's x plus delta x, that's only two terms. And there is a quicker way of multiplying those out. So this is kind of a shortcut. What I'm showing you here is the beginning of Pascal's triangle. Pascal's triangle is used for a lot of things, but one of its main uses for most people is to take a binomial to a power. It's basically a shortcut. And the easiest way to see is ones will go down this way and ones will go down that way. And what they do to get this number is they just add those two together. Just add those two together. So the next row should be one you can figure out. What should be the very first number out front? Well, a 1, and then followed by a. If you put these two together right here, it'd be a 4, 6, 4, and then what's on the end? A 1. There it is. Okay. And as you can see, this is a pattern that could go on forever. Right? You could sit here all day and continually go on with that, and we'll just go one more. Hopefully you see where the 10 comes from, where the 5 comes from, and where the 1 comes from. Okay. Now, just so that you know, is that the second number in will always tell you which one it's for. This is for if you want to square something, square a binomial. This is if you want to take it to the third power, fourth power, fifth power. Now this is probably going to take some time for me to prove this to you that this works, but once you see it in action, I think you can agree that it could save some time, especially when we start talking fifth power, fourth power. It can get kind of exhausting in a way. So I don't even, what's the first one I give you? X plus delta x squared, right? Well, let's just, this isn't a hard one. Let's just figure this one out kind of the old way. All right, let's just figure it out the old way first. So maybe just watch that, and then I'll show you how possibly once you get used to Pascal's triangle, it can speed things up. Okay, right? This is what we would normally do, right? Let's just FOIL it, right? So you would take x times x, which is x squared. You take x times that, which is x delta x, plus x delta x, plus delta x squared. Do you agree with that so far? So it'll be x squared plus these two terms can go together, right? 2x delta x plus delta x squared. Do you agree with that? And seeing there's a 1 here and a 1 there makes it very easy. Because do you see Pascal's triangle? And is it the correct row of Pascal's triangle? 1, 2, 1? Yeah, it is the correct row. So let me show you how you could use Pascal's triangle. Now this is kind of a, actually, believe it or not, x plus delta x is a simpler one. Once you start throwing other numbers in there, it actually gets a little harder. So be happy that x plus delta x will be the one we will be dealing with. So all you have to do is take that first term and take it to whatever power you're dealing with, which is the second power, right? And let's just take that last term and do the same thing. That one goes over there. Take the last term in. So now let's go back to Pascal's triangle. And what it's trying to tell you right here is what that coefficient of that middle term is what it's trying to tell you. So 2, and then it's x to the first and delta x to the first. Now let me explain it once we get done. Do you agree that all of the terms have 2 as their complete power? If you look at it all together, it is 2, correct? Because the 1 and the 1. Right? So you know they're all going to add up to 2. And are there any combinations? Because really I could write this as x squared and delta x to the 0, right? And I could write this as x to the first, delta x to the first, and I could write this as delta x squared and x to the 0. Are those pretty much all the combinations? 2 for the first one, 0 for the second one, like that? Is that pretty much all the combinations you can have? And that's really all you're doing. Whoa. Is that the same as what we had up here? So let's try cubing it without actually multiplying it all the way out, because we'd have to do that, agreed? Which I think some of us struggled a little bit on when we had that problem that we had to cube. Well, let's just go look real quick at Pascal's triangle. I think once we do this one, you'll see it. You agree that this is the row we should be looking at? Because I'm cubing it, right? So I'm just going to write that down. 1, 3, 3, 1. Agreed? So let's take the first term. It is x, and cube it. And I'm actually going to write out delta x to the 0 so you can see this pattern. You don't have to if you don't want to, but it might help you see this pattern later if you get confused. Plus. Write the 3 down. See this 3 right here? Write it down. And then do you agree we will have an x and a delta x of some kind? That's kind of how I look at it. You're going to have an x and a delta x of some kind because they're the two terms in there. And what you're going to do is the easiest thing is to take this power right here and take it down 1. So if I take that power down 1, now I'm at, and take this other power and take it, why? Because the total's supposed to be 3, right? You see that? Once you see the whole pattern, it'll make much more sense. Who believes after what you've seen so far, you can tell me what I should write down? Just the very next thing I should write down. Why a 3? Yeah, it's right here, right? Write down 3. And do you agree I will have an x and a delta x of some kind because of how you would multiply this out? You would have it's something in there, right? And based on the pattern, does anybody believe they can tell me the powers on x and delta x? Yes. 1 and 2. Very good. And I'm running out of room, and that's unfortunate. But plus. And you can write the 1, right, if you want, if that's going to help your pattern, right? 1, and I'm going to have an x and a delta x of some kind, right? And how about powers this time? Anybody else thinks they can do the powers? Follow the pattern? Yes. So 0 and 3, right? So how does this go? It goes 3 on the first one, 0 on the second one, right? And then 2 and 1, then 1 and 2, 0, 3. So you see how the first one keeps going down. The second one keeps going up. Can we clean this up? Because that's what we had in here. Multiply them. Yep. Just multiply them. Because that's the same thing we did here, really. Just multiply them. So what can I do for this first term to clean it up? X to the third. You don't need that. Because what is delta x to the 0 power? 1. Plus, can I really clean this one up much? Not really. And I know right now you're thinking, well, this isn't any faster than just doing the problem. And if that's the way it is for you, you can always just multiply it out. But I think once you get better at it, this is way quicker. But again, I think having variables in both of them is actually easier than having a number in one of them. And I think I show you a number in one of them next. Unless you would like to switch the next one to x plus delta x to the 4th. I'm game for that if you are. You want to just change number 3 instead of x plus 1 to the 3rd, change it to x plus delta x to the 4th? Because that's probably going to be more helpful to you anyway. So let's do that. We have the power to change that problem. Because these are the ones you're going to need for this chapter anyways. We will try that one to the 4th, though, and compare it to the one we have currently. So we probably better go back and find out what the row is for 4, huh? So 1, 4, 6, 4, 1. Whoops, one more. 1, 4, 6, 4, 1. All right, so you bring this one down. Again, really, if you want to, you can always put an x and a delta x. If you get tired of doing this every time, I think you probably know by now the first one and the last one are just going to be that to the 4th. Do you know that by now, or do you want to see the pattern still? See the pattern. All right. So what's this total for the power have to be according to this problem? Has to be 4th, right? So the 1 comes on down, right? 4 and 0. Okay? Plus. Yep, this 4 comes on down, right? 4, and you got an x and a delta x. What power should be on just this x here to shut it up? 3 and 1. Plus 6, and you know there's an x and a delta x because that's what's in here, right? And 2 and a 2. Okay. Yep, this 4 now. Oops, sorry, that 6 came from here. You probably all saw that. 4 x 1, 3. Yep, and then plus 1, right? And 0 and 4, right? So do you see, does the pattern I gave you before still hold true? Does the first one keep going down and the second one keeps going up? Okay. And basically what this helps us out with, it just gives us those coefficients to start with. That's what Pascal's triangle does. So to clean it up, I'm going to tell you, as far as test goes on something like this will not specifically be on a test. And what you're going to want to do is clean this up as much as possible for what we're going to be doing with it. Now you have to agree that would have been quicker than doing let's be honest, we'd still be working on that one. Okay. But that's the answer you'd get. Any questions on the pattern? Because I'm probably going to have to erase this to do the next one. But at least you'll still have it on your paper. This should prove to you that the second, having a number there is actually worse. Okay. Do you agree there's a variable here, delta x, right? So can I erase? All right. We're going to leave, well, not all that. We'll leave that up there. Because you agree we need to use the same one? All right. So now, up until now, it was x and delta x were our pieces, right? Now our pieces are an x and a 2. Okay, so I might use more parentheses this time. So let's bring down, we know we have an x and a 2, correct? And there's a 1 out front because of this. But x has to go to the 4th power and the 2 has to go to the 0 power. Do you see how that's different? But isn't it really kind of the same place that the x and the delta x were before? They really are. It's just it looks completely different when there's a 2 there. It almost looks as though we're doing it wrong. Okay. Now do you understand how I got that? Well, it's what's in here. You just multiply. Plus, what should I write? 4. And again, I'd suggest, kind of doing it like this, keeping it kind of neat and clean. 3 and 1. 6. And I'm getting smaller because I'm going to run out of room again. I thought I gave myself plenty of room, but apparently not. Apparently I write massive. But again, this is saying basically take x plus 2 times x plus 2 times x plus 2 again and times x plus 2 one more time. And so that would be a lot of foiling. Once again, is the pattern still there? It is. Okay. But without Pascal's triangle to give us the coefficients, we wouldn't know what to put out there, right? So what does this first one end up being, really? Yeah, because anything to the 0 power is just 1. So now, why does it make this harder? Yeah, you actually have to multiply stuff out, right? Before it was just x's and delta x's. We didn't have anything to multiply. But now, can I take 2 to the first? Yes, it's 2. Can I take that times 4? Yes, I can. It's 8. That's what that term becomes. So this one's done. Everybody see how that becomes 8x to the third? Because 2 to the first is 2 times the 4 is 8. Yep. And this number gets a little big. 2 times 2 is something you can do. It's 4. So 24. Once again, it gets kind of big. Just imagine if instead of a 2 in there, it was like a 7 or something like that. This would get kind of big. So 2 to the third is 8 times 4 is? Plus 16. There it is. So you see how that's not as pleasant. Again, imagine if that 2 was some other number. Or if it was a negative. It would take more time. On to the back. I'll probably do maybe... I'll look at 1, and then I think I might leave the rest of them to you. So we'll do number 5 together. Do you agree that x squared plus 1 is my function? Okay. And I'm asked to find the limit as delta x goes to 0. Have we done that? Yes, we have. Okay. But in the problems we've had recently, we had a's here, correct? And what do we do with the a? We replaced it with whatever number I actually wanted, correct? And maybe it was a 2, maybe it was a 1, who knows? But we're not going to do that. Now what we're going to do is find that general equation that'll answer me for any x value. Okay, it's basically a general formula for it. And that means you actually have to plug in x plus delta x, because that's really what this is saying. Substitute x plus delta x into that function. Then subtract the function. Right? We're going to go relatively slow, if that's all right. So it's saying plug x plus delta x. I should have started this way over there, but that's all right. Again, what we're really doing is picking some other point way out there that's nowhere near the x that I want, and we're pulling it back in towards the other one. We don't care how far out it is, but that's what we're doing. So I have to plug x plus delta x in there, correct? Which means in this problem I have to plug it in there. Agreed? So I will put this in red brackets so you can see where it goes. Okay? So x plus delta x is replacing that x right there. Okay? So I have to square it and then add 1. Is everybody okay with that first move, that bracket up at the top basically became that bracket down in the problem? Okay, is everybody good with that? So minus. Now what I'll do is I'll bracket it in blue. Okay. It says to subtract whatever the function is. Because let's face it, if I substitute x into the function, am I really going to do anything different than what I originally had? I'm replacing x with x. It's really what that says. So in other words, just write down the function. So in brackets, we have to write down. Now you can see, remember what I always told you about that location right there? After that subtraction, I always told you to put parentheses or brackets or something. Okay? Because you have to distribute this negative. Okay? All divided by, and remember, that's really was a plus delta x minus a, so it always just canceled. So here it's x plus delta x minus x is what it is. So can I substitute in 0 for delta x at this time? Why not? Dividing by 0. Is that a problem that kind of took care of itself before? Guess what? That problem is still going to take care of itself if you do the algebra correctly. Are there any questions how I got to where I'm at right now in this problem? Okay. So let's go x plus delta x and square it. Well, don't you have that written on the other side? All right, you have it, don't you? Or you could do it, of course, yourself, because you're all very, very smart. Do you agree that what I just underlined in black turned into what is written in black? Right? So now we have to, what's next? Plus 1, right here. Plus 1. If I were you, this would be a really good time to distribute that negative, if that's okay with everyone else. So I take basically minus x squared and, careful, minus 1. If you distribute the negative, right? Okay. I sure hope they do. Somebody just said they cross off. I'm like, I sure hope so. Because everything that doesn't have a what is going to cross off. What happened before? Everything that didn't have a what attached to it. Delta x went away, right? Magically. Well, does that still happen? Well, if we did it right, it's sure better. Or we did something terribly wrong. Okay, so the plus 1, you're telling me that goes away. Because there's a minus 1. Gone. Well, I have a negative x squared, though. Wow. Oh, yeah, out front. Negative x squared, positive x squared. Now, at this point, can I put 0 in for delta x? Am I getting a whole lot closer? Yes, I am. I still can't quite substitute in. I can't wait till I can. But there is a delta x in everything in the numerator. So it can be factored out. Okay. And if I factor it out, I'm trying to get it out of here and out of there, right? So what remains from this term I just put a box around is 2x, right? Plus, well, it's delta x squared, right? So if I take a delta x out, I still have a delta x all divided by delta x. What do you mean it goes away? Yeah, it cancels. Isn't that what we wanted to have happen anyway? Now what? 0 in for what? So can I substitute 0 in there? Ooh, can I substitute 0 in there? Yes, you can. And so once I substitute 0 in there, I get that the answer to this question is 2x. That is the slope. Garrett, if you give me an x value, I can tell you the slope at it now. Any x value that was on this original, any x value on that original, you give it to me, I can tell you the slope at it right now by simply substituting x into that little formula over there, 2x. Okay. So that's the nice thing. Remember before, could I ask you for 5 or 6 different x values? Then you had to do it 5 or 6 different times. Now I can ask you 5 or 6 and you do this once, and all you do is substitute in the 5 or 6 x values I gave you, and you're done. Okay. Now, if you don't believe me, do you agree x squared, yeah, that's great. X squared plus 1 looks something like that, agreed? And if I gave you, say, an x value over here at 5, do you agree if I went way up, that'd be pretty steep, right? And it's about what? It's about 10. What if I asked you at -1? You agree it'd be something like that? Oh yeah, it's going to be, -2. A little bit quicker, isn't it? Is it the same process you did for instantaneous rate of change? Yeah. Except you put in x instead of the number. So what I would like you to do for tomorrow is to do that exact same thing for problem 6, 7, and 8. Do this.